In this unit, we're going to take a look at alternating current and how it's produced by generators. Now, we've looked at DC current, and DC current, direct current, that's redundant, DC current, direct current actually means that it doesn't change with time. The current is always in the same direction and it's not varying. Generators don't produce a direct current. They produce an alternating current. And you'll notice instead of a split ring commutator like in a DC motor, I have two slip rings. And as this loop goes through, first it's cutting this way through the magnetic field lines, and then that rotates half a revolution around and it's rotating this way through the magnetic field lines. So it first cuts the lines in one direction, then it cuts the lines in the other direction, and we know that that means the current is going to reduce because first flux is increasing, then flux is decreasing, so that changing magnetic field is going to be it's trying to be maintained by the current in the loop. And so we can see when it starts out, if it starts out vertically, then as it rotates through the magnetic field and becomes more and more perpendicular, we get more and more voltage induced in it. Then as it gets less and less perpendicular to that field and more parallel, it goes back to zero. Then it reverses because now it's moving the other way through those magnetic field lines, and the same thing happens. So we get this nice sine-looking curve. And in fact, it is a sine curve. If we take a look at an animation of this, or not an animation, a drawing of this, we can see why it's a sine curve. And so this is that animation but drawn, right? So the green lines here represent velocity. The gray line represents that loop of wire that's moving through the magnetic field from north to south. It's rotating clockwise. And then I have these points on my wire. So this thing actually is a loop rotating through a magnetic field at a particular instance. And we know that the electromotive force induced in that loop is given by the magnetic field times the length of the wire cutting the magnetic field lines that's moving perpendicular to the magnetic field lines. Well, at this instant, perpendicular to the magnetic field lines is this way, even though it's moving this way. Since this angle between the magnetic field lines and our wire is this angle theta, then the perpendicular component of that velocity is v sine theta. So I'm going to go ahead and I'm going to make that substitution. I'm going to say the electromotive force is given by twice that, because this one's moving this way, this one's moving that way. They're going to induce this current in the same direction, and so voltage in the same direction. So there's two of them, that's the two. If there's multiple loops, then we have N. B, of course, is magnetic field. L is the length from A to B. It's not, you'll notice, this length. This doesn't matter. That one's not cutting field lines. It's moving, the force exerted on it is going to be to the side of the wire, and so it doesn't induce any current, it doesn't cut any field lines, it doesn't induce any current. Same with the backside. So only the lengths that are cutting magnetic field lines have a current induced in them. And so that's what L is. V, how fast it's moving, and then times the sine of theta. Of course, if theta is 90, then this is a maximum. If theta is 0, then this is a minimum. Now, if you remember from rotational motion, you can say that the velocity is equal to the angular velocity, omega, times the radius. Well, the radius is the distance from here to here. It's half the height of that rectangle. So I'm going to say that r equals h over 2. And the angle theta is given by the rate at which it's rotating times time, as long as everything's measured in radians. So I can make a couple substitutions. Theta is going to become omega t, which gets us how the sine is varying in time, or the voltage is varying in time. And then I'm going to replace V with omega r, but r has been replaced with h2. So 2nbl, that's all the same. V is now h over 2 omega, but h over 2 times 2 cancels, right? And now I have the height of the rectangle times the length of the rectangle, which is the area of the rectangle. So what I get is the voltage is equal to the number of turns times the magnetic field times the area of the loop moving through the field times the angular velocity times sine omega t. And that tells me the voltage at any point in time. Okay? You'll notice, because this is a sine curve, the voltage is at first going to be positive, and then going to be negative, and then positive, and then negative, which leads us to an alternating voltage. But since V equals IR, and V is alternating, it must be the case that I is also alternating. So we're going to go ahead and we're going to take a look at this in a little more detail. Power, voltage, and current. Okay? So like I said, the voltage is a sine curve. It alternates between plus and minus V max, or some peak voltage value. And that's given by this equation. So sine omega t times the maximum voltage equals the voltage at any point in time t. Now, if we would like, we can say that V equals IR, that's Ohm's law, and so we get I equals V over R if we just solve that for I, and so that means I equals V max divided by R times the sine of omega t. And if we make a substitution, V max divided by R is I max. So I equals I max sine omega t. Sweet. This is what we call the peak current. And if we were to look at that, we would see that it also is alternating at the same rate as the voltage. I should rewrite that where we can actually read it. So I equals I max, or peak current, times sine omega t. Now, the voltage is alternating plus and minus, the current is alternating plus and minus. However, power is given by I squared R, right? If we think P equals VI, but V equals IR, then we can replace V with IR and we get P equals I squared R. Well, what does that mean? Let's take a look at what that means. Okay, we're going to simplify this just a little. Power is given by I squared R. The power is never negative. However, it is sinusoidal because we get P equals I squared. Well, I, remember, is I max sine omega t. So I max sine omega t, it's a lowercase t. Well, this is squared, and this is all over R. Well, that means we're never going to have a negative power, but we are going to have a power curve that is varying in time. It's going to be a sine curve, but that sine curve is always above the zero line. And it's not constant power. What we're interested in is the effective or average power that an alternating current produces, which will allow us to find effective voltage and effective current from an alternating circuit. Because we tend to think of the voltage in the United States, you plug into the wall outlet, it's 120 volts. Well, that's actually, it's what's called the root mean square value of the voltage. It's not the peak-to-peak voltage. It is the effective voltage, because some of the time it's higher than that, some of the time it's lower than that. So what we're going to use is we're going to say, since the power's up here sometimes and down here sometimes, the effective power, or the average power, that's with the bar over the top of something, is equal to half of I squared R, I max squared R. Okay? And we're going to use that to solve for voltage and for current. So let's take a look at that. Okay? So if P equals 1/2 I max squared times R, then it's also the case, since V equals IR, we can replace the I with the V, and we can say power equals 1/2 V max squared R. And all we're going to do is we're going to solve these two equations for our own. These are our average powers, remember. We're going to solve these two equations for voltage and for current. But let's take a look at this. This is average power, and so this is a mean, right? This is the square, and so what we're going to get out of this is what we call RMS, or root mean square. So let's just go ahead and solve this thing. Okay, for I max, we're going to solve for I. So let's see, if I squared equals 1/2 I omega, or I max squared, and V squared equals 1/2 V max squared, then what we get is I is equal to the square root of 1/2 times I max squared. Well, that means I equals square root of 2 over 2 times I max. And V equals, these are average values, V equals the square root of 2 over 2 V max. Okay? And I say average values, but actually these are sometimes written as effective values or RMS values. So the root mean square or effective current in an alternating circuit is given by the square root of 2 over 2, which is 0.707, I naught or I max or I peak, and V RMS or effective voltage is given by 0.707 times the peak voltage or V max. Okay? So those two equations let us find the effective voltage and the effective current of an alternating current produced by a generator.